Good morning to all, and thanks for coming. I am Vicente Botet. I am working for Nokia in Lannion, in the west of France. I would like to talk about what product types are today and what they could look like in maybe C++20. We'll see what is the problem we try to solve, what are product types, the current situation. We'll see what the kind of algorithms that are applied to product types, and some additional constraints that make product types more usable. And we will finish by what could be done in the future and some conclusions. Okay, have you ever write something like that? I believe. Imagine now that you change your type, and instead of defining a structure, you define it as a tuple. The implementation will change. It is, I will say, less friendly, but it is a little bit more generic. It is working now also for stdri or C++ CRIs. Or it could work for CRIs if we define the tuple-like interface for them. Here is an implementation C++98-like for what this insertion on a stream could look like. We insert the left brace. We call to an auxiliary function, and we close the brace. The auxiliary function, it is implemented using recursion, and as the index of the element, it is now at compile time, we need to have them as parameters. The first parameter will be the index, and the second parameter is the size of the tuple. Then it is quite, I would say, quite ugly. It's something that we will like to improve, and we'll see something better later on. Anyway, we have here that with the tuple-like interface, we are able to have a generic solution for tuple-like types. So what are product types? Let's see, in Wikipedia, we say that a product type is a composite type of other types in which the order it is important. Okay? We know all that we have a lot of product types in the field, in the standard, in Boost, and what is more important is we have also that extracts are product types also. What we want to consider all these types having the same interface. Some of these types have all these elements have the same type, others are heterogeneous. And some types allow to have some kind of type constructors that allow to construct a similar type, changing either the number of elements or the type of the elements. And we will see that tuple is in some way the more generic one. And we have that when we are working with structs that are not templates, we cannot do that. We cannot change the number of elements, neither the type. Okay, let's see what we have as access for all these types. We have the well-known access using the field access for structs. You have index access for arrays and std array. We have tuple-like access for pairs, tuples, and array. And in C++17, we have a structure binding that allows us to extract the elements of, I would say, a product type, and it works now for C arrays, tuple-like types, and some subset of the aggregates. What we have now is that in order to provide this kind of access to these types, a lot of libraries, what they provide is a macro that will generate the needed instantiation of the templates and the overloading necessary to get all these types. And we have, for example, in Fusion that we can adapt an existing structure so that we will have a Fusion sequence access to this structure. And we can also define, and at the same time, the structure and the access. But what we have is that, for example, Bruce Hanna defined other macros because the access is a little bit different. Then, while this is in some kind, it's giving us some kind of reflection on the structure, we don't have a single interface to these types. So what structure binding gives us is a new assignment statement that allows to extract either by copy or by reference, or there are more variants of that. And we can use it to, in some way, emulate a function that returns multiple values. And now it is quite easy to extract the contents of each one of these values. The feature also has been adapted so that we have this extraction on the range-based loop 4, so that we can iterate over the element of a vector that support a structure binding and extract each one of the elements. So this, I believe, that is some kind of friendly user interface, and it is quite readable. As I said, structure binding supports C arrays, tuple-like types as customization point, and a subset of the aggregates, I would say C++14 aggregates, or structs that have all non-static data members public. In C++17, we have extended the aggregates so that we can inherit of non-virtually from other aggregates. But structure binding don't take care of this extension yet. We will hope to have it in C++20, but we are not sure how do we want it. If we want it as an additional member element, or if we want to take the elements of the base class as elements of the derived class. Structure binding gives us also the possibility to extract also bit fields. Even if a bit field has not a specific address, we cannot take the address of a bit field. With a structure binding, we are able to extract it, because a structure binding is giving us a name, just a name. However, we cannot define with the current customization point, that is the get function, we cannot customize access to a bit field because this function returns a reference to the field, and we cannot have the access of a bit field. Maybe we could think about having a bit field reference, a proxy, so that we could customize also for bit fields, but the current wording don't allow us to do that. So we have that structure binding gives us a friendly interface to extract the elements, but it is not generic enough to be used on generic algorithms, and we have that the tuple-like access is generic, but it is not so friendly. Then we'll see now what are the proposals that are ongoing on the standard committee concerning product types. This is the reference. Then we have on one side pattern matching for variants and tuple-like types. We have pack types literals with an extension of where we can use parameter packs. We have a proposal to have an access to the elements using some operators based on Python syntax. And we have something that looks like a tuple-like access, but that we consider also the types that are concerned by structure binding. Then pattern matching is a proposal that originally tried to address access to variant types, to some types. But it has also pattern matching on product types, on tuple-like types. And what we have is something that it is quite close to what we have with structure binding. We have an statement that allows us to extract the elements. There are much more functionalities with pattern matching, but I will not talk more about this pattern matching. I will say just that in order to customize this access, we have the proposal includes an extract operator on which we will have to say what is the address of each one of the fields. Then what we have is a different customization point, and we need to ensure that all the customization points will be equivalent, and we can deduce one from the others. This proposal tries to extend where we can use parameter packs. And you know that today we can use them only on expressions, and these proposals will allow us to define in an easy way this class tuple that will contain all these elements. One element, one field for each one of the types passed as parameter. And I believe that it is a proposal that is something that I will hope to have in the next standard. But sure, it needs much more detail. There's something that I like in this proposal is that we have given a type to an aggregate initializer. We have here an aggregate initializer, and we have associated to this type what we call a literal pack type. All of you, I hope you know initializer list, and we have this initializer list that it is the type associated to initializer where all the elements are of the same type. When we have a type that is different, it is an aggregate initialization, it is different. And having a type associated to each one of the expression of the language, I believe it is a good thing. We don't have it yet. Then, for example, using these literal packs, we can return also multiple values from a function. And what it is great on this proposal is that we can unpack directly this using pack expansion, as we do for parameter packs, and we will just forward all the elements of this pack type to this function. Currently, on the C++ 17 standard, what we have is that we will need to return a pair or a tuple, and we need to use the std apply function to call this function so that the apply function unpacks the element of the result of this calculate target coordinates function. Then this proposal simplifies in some way the code that we need to write in order to unpack these prototypes. This, again, besides the fact that the proposal says that we'll have a tuple-like interface for this kind of types, iterator-based interface, we need yet to have a new operator so that we can customize an operator, an ellipsis operator, expansion operator, that will allow us to expand these user-defined types. So that we have another way to customize. This is the operator that operator ... that will allow us to say I have my own class, my own struct, and I can define this operator so that I will be able to expand. Then, again, we need to be able to ensure that all these customizations are equivalent, and this proposal, it is not yet clear about how it works with CRIs or just structs that have all his non-static data member public. We don't know yet. But the idea is to have, I believe that the syntax is interesting, but we are working on that. Let's follow some proposals that are based on Python syntax in order to access the element to unpack here. And we have also the possibility to have some kind of a slice, taking elements from one element to the end or to another element. Okay. I name product type what it is supported by a structure binding. We need to work on the same set, and anything that it is not either a CRI, either customized with tuple-like access, either or something equivalent, okay? or that has not or is not a static data members public, it is not a product type. Okay? We have some predefined product types by the language, and we can customize it using the tuple-like access. This is what we have now that we name a structure binding. I want to name them product types, and I need a generic access to these types. Then, even if a structure binding is friendly, we need something generic. And currently in the standard, we have algorithms that like tuple-cat, std-apply, and some tuple conversions that work only for these types, tuple, pair, and array, only for the standard types. It is some implementation have implemented these functions so that they work for any tuple-like type, but not the standard don't require it. And I believe that we need to make them work on all these product types. And again, I would like to have an access with literal packs types, but it is not yet clear how it covers all the product types. Then a product type is just something that we know the number of elements, we know the element type associated to the elements, and we have access to the elements of a given instance. And let me use this notation to say I want to access a given element of a product type, and I have used it explicitly a namespace product type in order to be explicit. It is not a get that do anything we don't know. It is a get that gets the element of a product type. As you see, we are defining in some way a concept. We are defining the concept that has access with these functions, get, size, element, and of course, we will expect to have some kind of threads that allow us to check if a type is a product type. So we will have as is product type threads. Okay, let's see some algorithms that work for product types. There are a lot of them. We can do for each. We can do a hash on product types. We can do swap. We can compare product types. We can accumulate for left or for right the contents of a product type using a given function. Let's see how swap could be implemented with C++17. We have the swap function that will call to an auxiliary function here, swap implementation, on which we will pass the index of the elements of this product type. I have used for that an element sequence for so that we have the index associated to this product type, taking into account the size. Then here I have an error. I am missing here the, it's here, okay, size B. Okay, we have then that we are passing the indexes of the product type, and now we are able to use fold expressions so that we are expanding we are expanding here using a fold expression with the comma operator, and just we are calling to the swap of each one of the elements. This is the best we can have today with C++ 17. With pack types, it could look much better. We will not need to use this tricky to pass to an auxiliary function the index so that we have a template parameter that we can expand on. All of you, do you know the index sequence? All of you? No. Wow. Okay. An index sequence is just a sequence that has as parameters the integers 0, 1, 2, 3, 4. Then when we have this template parameter, we are able to expand on this parameter y. And here, when we have this expression, product type get y, and we expand using the fold expression, we are taking each one of these instances so that we are doing all the swaps one after the other. So if we are able to define for all these types functions like cat, apply, and make from, we can define the existing ones that work with a subset of these types so that they work, this function work for all the product types. Well, what's happening? Okay, let's see today on the left, we have some constructors and assignment for the class tuple. And we have a lot of them because we are, in my opinion, too specific. We have constructors to construct from a tuple, on which we have types that are convertible to the types of the tuple. The same thing for pair, assignment, and the same thing for allocators. If instead to be specific, we accept to be constructed from a product type, we have just one function. So very more generic, allow us to have less code with more software. Luis?
You would still need to constrain on the fact that the elements of the tuple are constructible from the elements of the product type, because otherwise, if you try to assign, say, tuple int char bool and then product type with stud strings in it, it won't work.
I have not added the constraint, but the types need to be constructible, either in this case, either in this one. Okay. And in the same way, we can be more generic and have less software, less code. We could also give other assignments for pair that are missing, so that we can assign any product type with two elements that have elements convertible to the elements of a pair. We can. This is a conversion that it could be useful in some cases. Okay. Some algorithms need to work with functions that I will name here, n functions that are overloaded on n types. Example of these functions are, for example, for each that will do something on each one of the elements of the product type, transform that will apply a function to each one of the elements and return the product type of the results. Folding, again, we will have a initial state, and we will apply a function to each one of the elements. Then we have this need of overloaded, overloaded function. And we can do it today with classical function objects and adding overloads. We can do it also with generic lambdas. We can do it also with, we could maybe do it also with a feature that could be, I hope will be part of the next standard overload set. So syntactic sugar feature we will see more. That allow us to have this kind of overload. And what I proposed some time ago, an overload function that takes n functions and with a function object that overloads on all these functions. Okay, the same thing, the same structure always in order to work with this kind of types, product types. We define a function for each, and we forward to an auxiliary function given the indexes of this product type. And we use some kind of expansion here. Here, for example, for each, what I would expect is that the application is done in a specific order. I will expect that the application of 0 is done before to the application to the index 1 and so on. And then for that, we could use initializer list, because initializer list ensure that the order is preserved. If we wanted to have a for each that don't have this constraint, we could use something else. To call to a function that, so that we don't have this constraint on the order of the call of these functions. And here, I have not used invoke, but it is the thing to do here. Invoke this function, and we are taking each one of the elements, and we call this function to each one of the elements. And here is a tricky to return 0 so that we have an initializer list of ints. This is just to be able to initialize this expression. And now, for example, we can do that. We can do a for each for each element in a product type, and insert on a stream or whatever you want. Here we are using a generic lambda, so that the parameter is something as if we had a template. Okay, we have talked up to now about access, but we want also to have a coherent initialization and construction of product types. A product type, it is, I would say, aggregates and product types are very close. Then I will expect to have that product types accepts any aggregate initialization expression. And most of them support this kind of initialization. However, we have std array that need this nest brace, because std array is trivial and don't define the constructor from an aggregate. Then we need to add additional nested braces to initialize the real C array that it is inside. I believe that it will be great if we could have the same syntax for all of them. And we want to be able to return product types also from functions. And unfortunately, we are in C++ and C, and we have CRIs. We are unable to return CRIs from a function because CRIs don't copy. CRI copy only the pointer. Then we are unable to do that. Then when working with generic, you want to do something generic, don't use CRIs, use std array instead. Anyway, I believe any one of us prefer to use a std array than a CRI, and we don't lose on performance. And here are some examples of algorithms that need to compose this, to create new product types. You have cat that will return a new product type, or transform, or a lot of more of them. Okay, then in order to construct these product types, we have in C++ 17 something that is very useful. We have this feature, template argument deduction for constructors. Today, we are able to deduce the templates for functions, template parameters for functions. But for constructors, we were not able to do that. And now we will be able to construct a pair just giving the two elements. We will deduce that A has a type, B a type, and we will construct a pair with the associated types. But we have that pair, tuple, and array are templates, but not all of the same type. Pair is a template with two template parameters, two type template parameters, tuple a variadic number of types, and array is a template with a type and a number. Okay, then if we want to write generic algorithms, we cannot use this feature, that it is useful at the user side, but for generic algorithms, it is not enough. Then I proposed some time ago to have a generic factory. We have not yet reviewed this proposal because we are trying to finish C++ 17, and we are fixing bugs. And this generic factory will allow to take care of this problem. And for that, we have a make function that takes as parameter either a template, either a type, either a type constructor. Once we have this possibility to construct product types, we are able to do a lot of things like that. Transform, chain. This is a way to name and bind for monads. Filter, cat, prepend, flattening a specific nested product type, dropping elements, and it depends on how we are able to do that. If we are able to construct a new product type with a single element, what we have is that a product type of this kind will become a functor because we are able to define the transform function. Or we can define an applicative interface because the lift function will just be make. And of course, we can define a monadic interface for these product types. If we have that the make supports the ability to construct with a varied number of elements, we are able to define functions like insert, prepend, append, drop, remove, and being able to define this drop from function make this that product types are could model the HANA iterable requirements or the HANA sequence. Then we see that with not too much things, we are getting a lot of algorithms that work with product types. And last, if we will have a monoid also, then this is a structure that is very rich. Then let's look at how this transform function could be defined. We define transform so that we have two definitions, even there is yet a third interface on which we take a template, and we will use an auxiliary function transform that will take a time constructor. If the product type itself is type constructible, we can use it also. And here just this auxiliary function, what it would do is to call to make, invoking each with this function with each one of the arguments. We are constructing we are constructing here a new product type with these elements that are expanded here. Okay, then only with having a product type access and being able to construct these types, we have a lot of algorithms available to us. And here is a specific use when we have a tuple is a type that is able to construct with a varied number of arguments. We are not able, we don't need to be more specific, and we will get a tuple of strings here. However, if I have a point, and maybe point is a struct, then I cannot transform this point in another point of strings. So I need to give here what is the product type I want to build. Then here the result of this transformation will be a tuple with the string associated to each one of the elements of the point. Here is some of the numbers ANA algorithms associated to each one of the concepts ANA has defined. Product types are another way to access these types. And all these algorithms are applicable to product types as I have defined them. Here are some algorithms of boost fusion that has a different interface to access them, but once you are able to define this access interface, we retrieve all these algorithms. And I believe that I would like to have something rich as this in C++, not only in Boost. Let me finish with some examples. Is unique represented is a trait that defines if a type has not padding between the different elements. And we can define it using this fold-left function so that we are accumulating the size of each one of the elements. If the size of the product type it is the same as the sum of the elements, this means that we don't have holes between them. This works. This don't work in some cases. This don't work with bit fields, because bit fields, the type element of a bit fields will be an integer, and the size is bigger than the size used by this bit field. Then, when we don't have bit fields, this is a way to implement this thread. This thread it is something that is useful to define hash functions, so that when we don't have any instance of our type is represented by a sequence of bits that is different, we can use just the sequence of bits to generate a hash function. Okay, take. I will split this function. We could split this function. First, we can transform the product type in a product type that has the size of these product types. And then we can fold left just adding them. And we see that we have something that is quite similar of what we have with ranges. And we can apply these functions using some pipe notation, and we could have things like that. We transform and we fold. With the function, the feature overload sets, we could have things like that. This will mean the overload set of the additional operation, and this will not work for size of, I believe, but you see the idea. Okay, the other example is the stream, and we see a implementation C++ 98 like. You can see it now with the use of fold. If we have a fold left index function that allows us to accumulate things using the index, then we can define this stream insertion of a product type just by accumulating on the output stream, and if the here we are passing an index that is something that is a integral constant, and then we can get the value of this integral constant, and if it is different of the 0 element, we will add a comma. Then we see that with this kind of abstractions, we reach to write shorter functions using the algorithms that are available for these types. There is something that it is on the everyone is talking about, this problem of cache. We need to ensure that we have the elements we are working on the cache. And when we work with product types, all the elements are as in a structure. Then we could have a structure with elements C, X, Y, dx, dy. And if the algorithm needs only C, X, Y, we are having all these data that is occupying the cache and it is not used. Then what I mean is that product types are well, but sometimes we need to move to a structure of arrays. And having the ability to introspect the product types, we are able to move from one to the other. Then just give some reference of some links. There is a library scatter that is based on boost function that allows to do that in a clean way. I believe that it is worth taking a look. And there is a blog of Jose Maria Lopez Munoz that define a way to access to this structure of arrays in a way that it is something really interesting. Just here, I have added here, just for reference, it is worth taking a look. Okay. There is a lot of work. Summarizing is we need to have more on eager algorithms, heterogeneous sequence. There are prototypes that we want to have them tagged with, as a structure has names for each one of the fields. There are work that is already done on with Boost Function, Boost HANA, Range CS also. And this is something that it is done for ranges and Boost Function. We have views on sequence. And this is needed because when we are constructing new product types, we don't want to copy them. We want to do that in a lazy way, so that we can perform better. Then I believe that Luis has started working on that for Boost HANA, and I believe that all these things are useful for any one of us, and why not to have them in the standard. Then, just to finish, prototypes, I would say, are everywhere, are very rich, with a lot of algorithms that applies to them. And in order to make it possible to have this on the standard, we need a unique and generic interface to them so that we can build on top of that. That's all.